Okay, I want to continue on with the last video. I was trying to tell you how you can use the molar mass as a conversion factor if you have to convert the grams into moles or moles into gram, which is what I'm going to show you in subsequent slides. But either of those two can be used as a conversion factor to do the needful. All right, so let's first realize, let's understand what do we mean by mole and how we can apply that concept. Let's say the question is that you are given a mole of sodium carbonate, which by the way is Na2CO3, and realize that carbonate is CO3 to negative. Let me just write that somewhere. CO3, and 2 negative is the charge on that. So I'm just going to say that as to the power of 2 negative is the charge. And you have sodium Na, which has 1 positive charge. So when you are trying to get a formula containing both of those, that 1 is going to come on the as a subscript for the carbonate, and 2 is going to come as the subscript for sodium, and you get your formula as Na2CO3. So if somebody asks you for a given mole of Na2CO3, how many sodiums and how many carbonates are present, you would say that since each Na2CO3 is going to give you 2 moles of sodium and 1 mole of CO3 to negative. That means that if you have a mole of it, it is going to give you 2 moles of sodium and a mole of carbonate. Each of those Avogadro number, the 6.02 times 10 to the 23rd, is going to give you twice the amount of sodium and the same amount of carbonate units. Now, like I said earlier, if you know the molecular mass, you can simply write down that numerical value, and the units of that would be grams per mole, but that will be called as the molar mass then. So if you were to determine that for, let's say, something like HCl, all you have to start doing is get the mass of hydrogen, which you can say 1.0079, plus the mass of chlorine, that will be 35.5, and you simply just add the two. So it's going to be 36.507.9. And in terms of significant figures, if you wanted to go by that, you will need to report the least number of significant figures. You're going to write this as 36.5 grams per mole, because that will be the molar mass for the compound. Of course, in terms of molecular mass, this number will be 36.5 AMU. So, all right. Let's take it forward. Let's go forward. The question here is that you're supposed to calculate the molar mass, and you're given the first one is Fe2O3. So again, your aim is to determine the molecular mass or the formula mass and report it in grams per mole, and that automatically becomes the molar mass. So all you got to do is read the mass from the periodic table for iron, and the one that I have is saying 55.5. So 2 times the 55.5 for iron plus 3 times the 15.9994 is going to give you, when you work the math for that in accordance with the significant figures here, that will give you the final answer at 158.9982. And if you think about the decimal figures, you're going to go by what's given in the data. So since the first one has only one significant figure, once more time, 158.9982, didn't take it the first time for some reason. You're going to just simply report up to the first decimal point, so you can just simply round it up to 159.0 grams per moles, because this is molar mass. Likewise, you can perhaps work on the second and the third values. Again, all you gotta do is pick the atomic mass, the fractional number from the periodic table, and multiply that by the number of atoms of each kind, add them all together, report it in grams per mole, and that will be your final answer. All right, so let's take a look at another molecule we have here, Li2SO4. If somebody can give me the name for that. Yes, indeed, it is lithium sulfate. Lithium sulfate, that is the name of this molecule. The question here is, how many Li2SO4 units are there in 3 moles of Li2SO4? So one can simply say that, in a sense, 3 moles of Li2SO4 will contain 3 times 6.022 times 10 to the power of 23, which by the way is the Avogadro's unit, that many Li2SO4 units. So 3 times Avogadro's number, let's just write the shorthand as well, 3 times the Avogadro's number, and is going to be the total number of Li2SO4 units that will be present. The next question is, how many lithium atoms are in 3 moles of Li2SO4? Well, for 3 moles of Li2SO4 units, you know that each Li2SO4 unit gives you 2 lithium atoms. So since I should just write it this way, 2 lithium atoms are present in, so I'm just going to put an underline for that. Let's see, underline. If only I can show that very easily here. Okay, one more time, I'm gonna try that. Okay. So here, because I want to say that essentially for each lithium sulfate units, I have 2 lithium atoms that are present per lithium sulfate unit. So I wanna just, what's going on? Okay, for some reason it won't allow me to use the underline here, and I don't know why, but anyway, what I want to tell you is you can use the dimensional analysis method. So you can say that since there are 2 lithium atoms per mole of Li2SO4, so instead of showing the underline, I was trying to show you exactly what it'll look like, but per means the same thing. So the mole of Li2SO4 will cancel off, and you would essentially get 6 times, because 2 times 3 is 6, 6 times the Avogadro's number is going to give you the total number of lithium atoms that you're going to get out of 3 moles of Li2SO4. Likewise, you can do the same thing for sulfur. Each Li2SO4 unit is giving you only 1 sulfur atom. So 3 moles of Li2SO4 is going to give you 1 sulfur atom. So realize that you can use again the dimensional analysis method in order to figure this out for yourself, and that will come out to be just simply 3 n, 3 times the Avogadro's number is what you're going to get at the end of the day. The last one is how many atoms are there in 3 moles of lithium sulfate, where these atoms are oxygen atoms. So since you have, again, let's write that, since you have 3 moles of Li2SO4 units, and each Li2SO4 gives you 4 oxygens. Hence we can say, and that's coming out as a per mole number, we can simply say that 12 times the Avogadro's number will be the number of oxygen atoms that you're going to get at the end of the day. Now, depending on the question, if I want you to calculate in an exam, if I want you to calculate all the way, please plug in those numbers, plug in the value of the Avogadro's number, which is 6.022 times 10 to the 23rd. Plug in that value so that you can calculate for yourself the overall number. I probably will run one of those for you so you can, kind of compare your answer and make sure that you have the correct values and you're calculating it right and you're expressing it in a correct manner. So I'm going to do that for basically one of those. And the numbers I'm getting are to the tune of 3.61 times 10 to the 24 for the case of lithium, 1.81 times 10 to the power of 24 for the case of sulfur, and 7.26 times 10 to the 24 for the case of oxygen. So you can calculate these in your own time and compare if you're getting ballpark the same range or not, so that you know what the correct answers are. All right. The next question is, well, the point is that why should you know moles? Why is that important? And I want to kind of take you back to what I was discussing earlier. I mean, if you think about it, you can't really isolate one particular atom and go to the scale and just put it on the scale and try to calculate the mass of that one atom. So what goes on at the microscopic level, on the microscopic scale, and what's going on at the macroscopic scale are essentially, two different things, and that's what I want to kind of highlight here. So if the question is what is the mass in grams for chlorine atom, how can you determine that? Well, from the definition of mole, that if you have taken a mole of chlorine atoms, that will contain 6.02 times 10 to the 23rd chlorine atoms. So if you have and that weighs 35.5 grams. So you can say that 35.5 grams correspond to the Avogadro's number, 6.022 times 10 to the power of 23. That's what it corresponds to. And so if you have one atom, so these many atoms, and if you have one atom only, how much will that weigh? So all you have to do is divide the 35.5 grams by the Avogadro's number, and you will have your answer in grams per atom. So let's give it a shot in terms of what it would look like. You are given 35.5 is the grams per mole, and so when you subject it to the dimensional analysis method, you would say that 1 mole contains essentially, let's see if it allows me to put the underscore. For some reason it's not letting me take the underscore part. So I'm just going to write that as 6.022 times 10 to the power of 23. And that's how you would, since 1 mole contains that many atoms, you would be able to figure out the grams per atom. If you are a unitary method fan, you can also do the same thing. It exactly means the same thing. You can do that using what is called as unitary method, and you can say that the Avogadro's number, 6.022 times 10 to the power of 23 atoms that make up a mole, essentially, that make up a mole, correspond to 35.5 grams. And now if it was only one atom that I wanted to find out the mass for, in your head you can